That's just keyword because I have to swap into English. But you know, this talk is going to be held in English. So even those who are not so much interested in English, they will benefit a little bit because at least it will be some further education in a foreign language you all love dearly, I'm sure. Our most distinguished guest and world-famous mathematician, of course, is Dr. Kaloyan Slavov. Thank God, his name is on the board, otherwise I have problems remembering it. He's going to give a talk about double counting. Of course, you all know what it is, at least I know what it is, no, I haven't got a clue. But that's the reason why he's here. He's going to make you delve into this topic. I hope you will enjoy it. Thank you very much.
Thank you very much, Mrs. Stefan, for the invitation. Thank you everyone for coming. I'm really happy to be here because Balis is one of my favorite cantons for hiking. I've done a lot of hiking here, mostly along the southern facing slopes of the main valley. But actually, when I also did some hiking along the northern facing slopes, then I got my second perspective of the valley. Then I learned really well the geography of the region. And the purpose of my talk today is to illustrate how useful it is to have a second perspective also in mathematical problems. Consider a country which has 7 cities. We represent them as 7 points. Some of the cities are connected by a road. If you have 2 cities, they are either not connected or connected by 1 road. The number of roads out of each city is known. The mayor of each city knows how many roads go out of their city. These are the numbers. There are 3 cities with 3 roads out of them, 2 cities with 4 roads out of them, a city with 5, and a city with 2. When I say out of each city, I can also say into each city. Doesn't matter. The roads are both 2-directional. Okay, the mayors gather together. They only know the number of roads out of their own city. They don't have a map of the whole country. They don't know where the roads go. They only have a very local picture. They know their city and a little bit nearby. They know that there are 2 roads, for example, leading out of that city. They don't know where they connect with. The question is, what is the total number of roads in the country? They have to figure out the total number of roads. They gather together, they have this information, they basically have the numbers 333, 2544, and from those 7 numbers, they have to determine the total number of roads. Can anyone answer this? Yes?
There are 12 roads.
12 roads, yes, perfect. 12 roads. Does everyone agree with this 12, this answer 12? Are there other answers? Who thinks the answer is 12, indeed? Okay, not everyone though. What do the others think? Someone else? Not everyone thinks the answer is 12. Okay, so let's look. Of course, you add all of these numbers. 3 plus 3 plus 3, 4 plus 4, 5 plus 2. And this is equal to 24. Are there 24 roads in the country? No. Why not? Yes?
Because they go in and out.
Because every road goes in and out. Every road connects 2 cities. Very good. Thank you. Thank you. Thank you. This number 5 there does not mean, well, what is the meaning of this 5? There are 5 roads that go out or into that city 5, labeled with 5. And so the meaning of this 24 is that if you draw a mark next to each city on each of the roads, you have 24 marks. 24 is the number of marks, not the number of roads. This is the number of marks. However, if you look at the row, as you say, a road goes in and out, it receives 2 marks. So every road is counted twice in this sum. Therefore, the number of marks is twice the number of roads, and correctly, the number of rows is 12. Indeed, notice here that we counted in two different ways the number of marks. On the one perspective, from each city, going city by city, adding up all of the contributions. On the other hand, thinking about the roads, each road receiving 2 marks. Okay, excellent. So this is our most basic example of double counting. Now consider a cube. It has 12 edges, 4 on the bottom, 4 on the top, and 4 vertical. Prove that you cannot put the numbers from 1 through 12 on the edges of the cube. The edges are these segments joining vertices. So that the sum of the 3 numbers on the edges out of each vertex is the same. If you look at A, it has 3 edges. B has 3 edges. If you add up the 3 numbers, can you always get the same sum for each of the 8 vertices? Prove that you cannot arrange the numbers from 1 through 12 in this way. Of course, you can start, you can try, you can say, okay, I put a 7 on AB, and then I put 5 from A going up. At some point, you get stuck. But let's prove that this is not possible. You cannot arrange the numbers from 1 through 12. Well, suppose that you can place them. Suppose that you place them on the edges of a cube in any way. Not necessarily with the same sums on each vertex. And consider the sum of the 3 numbers on the edges out of A. You look at one of your vertices, and let's count the sum of the 3 numbers on the edges out of that. It's like from the previous problem, the mayor only knew how many roads go out of their own city. So A keeps track of the sum of the 3 numbers going out of A. Similarly, you define SB up to SH. For each of the 8 vertices of the cube, you count that sum. You compute the sum of the 3 numbers. And now, you can take the sum of these 8 numbers. When you put them together, you create this symmetric quantity. It's symmetric for the cube. There is no preference for one vertex over another. If you just pick a favorite vertex, you cannot say anything from that vertex. Of course, who knows what the sum is. But when you put them together, can you tell me what you get when you add up all of these 8 numbers? Take the contributions, the sum of the edges from the first vertex, then the sum of the numbers on the edges from the second vertex, and so on. What do you get at the end when you put them all together? The numbers from 1 through 12 are written down on the edges. I don't know what number is written on AB, or on the edge from A going up, or from A going back, but I add these 3 up. And then I add up the 3 numbers from B. From B to A, from B up, and from B back. And then I sum up all of these 8 numbers. What do I get? I have no clue about the 3 numbers from A. But when I add up all of these 8 numbers, what do we obtain? Yes?
24.
No, 24 was in the previous problem. 24 was in the previous problem. Okay, try another guess. Try another guess. Try another guess. Think about 7. 7 is written somewhere on some edge. Okay, you agree that, yes?
234.
134. Okay, so you get, well, not quite, but maybe the multiplication wasn't exactly right. Think about the number 7. 7 is written on some edge. Imagine that 7 is written on the edge AB. Well, when you compute the sum of the 3 numbers from A, you have 7 as one term. 7 contributes to that sum. When you compute the sum of the 3 numbers out of B, 7 is also a summand there. So 7 appeared as a summand twice. Each of the edges the number written on any edge appears in this summation twice, once from each of the two ends of the edge. Exactly as in the previous problem with the rules. It's just slightly, there is a slight twist here that you write arbitrary numbers on the edges of a cube. So the number written on every edge appears twice. And when you add up the numbers from 1 through 12, I don't know exactly what number is written on which edge, but when I put them together, when I add them up, they are the numbers from 1 through 12. I multiply by 2, and this is 12 times 13, 156. I'm sure that's what you had in mind. Now, tell me though, is it possible that all 8 of these numbers are equal? That all 8 sums from each of the 8 vertices have the same value? Can they all be equal? If yes, what should they be equal to? Is it possible that SA and so on is equal to SH? All of them are equal on the left-hand side. Can they all be equal? You know that when you add them up, you get 156, 12 times 13. Can these 8 numbers have the same value? Can they all be equal? Yes or no? No? Very good. Why not? Why not? If they were all equal, what would they be equal to? If you have 8 numbers on the left and they're equal, it would be 8 times that common value is 156. What should they be equal to then? Yes? 156. That's right. Yes?
39.
39. No. See, if they were all equal, then 8 times this common value would be equal to 156. But this is not divisible by 8. This number there is not divisible by 8, so the numbers on the left, they cannot be all equal. That's why you cannot put the numbers from 1 to 12 on the edges of the cube. Okay? You ask yourself, if you could, what should that common sum be? From each vertex you should get the same number when you add up the 3 numbers on the edges, but what should that common value be? You compute, it cannot happen, it wouldn't be an integer. So they cannot be all equal. This is another example of double counting. On the one hand, we computed the sum of all the numbers, looking at them vertex by vertex. From each vertex, you look at the contribution. From the other vertex, you look at the contribution, going vertex by vertex. On the other hand, you go edge by edge. Each edge is counted twice, once from each vertex. Okay, now consider a 6 by 6 board. Tiled by 2 by 1 domino pieces. This is one example. Tiled means it's covered so that the pieces never leave the board and never overlap. This is one example of a tiling. Prove that the board can be cut by a line which breaks none of the domino pieces. Imagine each domino piece is very precious. You don't want to break any of them, but you want to cut the board into 2 not necessarily equal parts. What is an example here of such a line? Is there such a line on this example? Yes? The bottom, yes. Here on the bottom there is a line. On this example there is only one such line. You can imagine if I was doing an easier arrangement of the dominoes, you would have many such lines. But in any case, no matter how the board is tiled, prove that there is always at least one line which cuts the board somewhere and breaks none of the pieces. That's not easy. So we have to give a proof now, and the reason is tricky. It's tricky. You don't know how the board is tiled. There are many ways to tile the board. You cannot go over them case by case. There are way too many, and plus you want to give a more elegant, more conceptual proof. So you don't know, you have no idea. All you know is that the board is tiled in a certain way. Okay, so now here we change perspective. This is the double counting thing. You change perspective, you look at it from the northern facing slopes. Right now, the setup is the board is tiled, and then you have to work hard. You have to figure out how to find a line, a special line. So you somehow try to fit a line. Rather than thinking this way, let's first consider a line, and then think about how the board is tiled. Change perspective completely. Rather than you having a tiled board and then trying to find a line, draw a line and then think about the tiling. Okay, suppose that each of the 10 candidates for a line, you have 10 possible lines that could do your job. You see, you have 1, 2, 3, 4, 5 vertical and 5 horizontal lines that are candidates for your desired line. At the end, you want to say that one of those 10 lines should work, should cut the board without breaking a domino piece. You have 10 candidates for a line, and suppose that each of them breaks at least one domino piece. You start with the line, and now you build a domino piece. So now, starting with the line, you say something about the tiling. You suppose that it breaks a domino piece. Okay, from here, can you continue the argument and make a further statement about the tiling of the board? Can you say something else about how the board is tiled? Can you locate some other domino piece? Can you tell me that some domino piece must be somewhere, or must not be somewhere? Anything. Can you make any further observation? This line cuts a domino piece. Suppose that every line cuts some domino piece, yes?
At least one needs to be vertical.
At least one needs to be vertical. Yes, it cannot cut 6 domino pieces. Well, why not? Why can it not cut 6 domino pieces? And then on the left you would only have vertical ones. Well, yes, in this particular case, some domino piece somewhere on the board has to be vertical. But tell me about the relationship between this line and domino pieces. What happens close to that line or near in this region somehow? Give me some further interaction between the line and the tiling of the board. Yes?
You can start, but just like over there, you have to left one. You can start.
You could start by building a domino piece from the bottom left going up.
Yes.
That's true. Yes. Yes, but the thing is there are many other ways that the board could be tiled. Tell me something that will happen for sure. Yes.
You can draw another line and then you split another domino piece.
You can draw another line and.
Then you split the next domino piece.
And then another line will also cut some other domino piece. That's right. So any line will cut a domino piece. Suppose that. We should get a contradiction. Suppose that every line cuts a domino piece. So you're saying if I draw another line, it will also cut a domino piece. But let's continue further. Let's go a little bit deeper about that particular line. You have a line, it cuts a domino piece. Can you say something further? Can you say something more? Yes?
You know that on left and the vertical
Uh-huh.
and you can't put all the other pieces like horizon, like this.
Yes,
And you
horizontal.
can't put all of them in one line, like from the left to right. You have at least one domino that is vertical.
You need to have at least one domino that is vertical. Yes, somewhere you have to have a domino that is vertical. But can you tell me something about this line in relation to domino pieces? Some connection with that particular line? You're saying that you cannot have the dominoes all horizontal. Yes, we had this comment from before. Can you look? Yes? At least one more domino piece has to be cut by that line. Excellent, thank you. This line. A line cannot break just a single domino piece, because look at this. If the line breaks only this domino piece, on the left of the line, I have an even number of squares, and with this square from that particular domino removed, we are left with an odd number of squares. And the left side of the line, you cannot tile the remaining squares by domino pieces, because now you have an odd number. The board, don't forget, 6 by 6, even lengths. On the right, similarly, it's an even number, in this case 4 by 6. So the line cannot cut just one domino piece. If a line cuts a domino piece, it must cut yet another domino piece. It must hit a second domino piece. This is the crux of the matter. This is the meat in the solution. If you assume that each of the 10 candidates for a line breaks a domino piece, then each of them has to break at least 2 domino pieces. You cannot get away with breaking only one domino piece, because then you cannot tile the left, you cannot tile the right. Okay, can anyone finish from here? Yes?
Well, so we have 10 lines that each have to break 2 dominoes.
Excellent.
But on the 6-on-6 board,
Yes?
we have only 18.
Excellent, excellent. Thank you, thank you, thank you. That finishes now the proof. Okay, each of the 10 lines breaks at least 2 domino pieces, and that will make it for 20 domino pieces, because a domino piece can be broken up by only one line. You cannot have 2 different lines break the same domino piece. So each of them breaks 2. The first line breaks 2, another line breaks again at least 2, and those 2 are different from the first 2. Third line will break further 2. Altogether, their lines will break at least 20 domino pieces, but on a 6 by 6 board there are 18 domino pieces. You see, we counted the domino pieces from a completely different perspective, not from thinking of a 6 by 6 board. Of course it has 18 domino pieces. We counted the domino pieces from the point of view of the lines, and each line breaking a priori 1 domino piece, and then further a second domino piece, and this requires at least 20 domino pieces. Contradiction. Again, this is an example of how you finish the argument by thinking first about the lines and then the tiling. Okay. Peter marks 20 points inside the square, as well as its 4 vertices. Here I'm going to draw an example with 5 points inside to simplify the drawing. Then he connects some pairs of marked points by straight line segments. So he draws straight line segments, no 2 of which intersect outside of those points, and so that the square gets divided into triangles. We say that he triangulates the square, something like this. From this he builds a net of triangles. So 20 points, and then he builds this net. Question, first question, which is a very natural question: how many triangles does Peter obtain at the end? From these 20 points, when he connects them and triangulates the square, how many triangles are there going to be? That's one question that you may be interested in. Now, of course, this question right now is not even asked in a precise manner. How many triangles does Peter obtain? It's even more interesting to ask, does he always obtain the same number, regardless of how he chooses the 20 points? Maybe for one choice of 20 points, he obtains a certain number of triangles, but then the next day he chooses 20 different points and obtains a different number of triangles. Or, if he chooses the 20 points, but then he has further choices of how to make the triangulation. You see here, you have many choices of which dots to connect. Maybe for the same 20 points, he could get different numbers of triangles depending on how he does the subdivision. So does this number depend on the way he chooses the 20 points, or on the specific triangulation? Yes?
No.
No, very good intuition. No matter how he chooses the 20 points and the triangulation, he always gets the same answer. Why?
Because the lines don't cut each other.
The lines don't cut each other, that's true, yes, the lines don't cut each other. Yes?
They cannot, because
That's true, the lines cannot cut each other, that's true. But the thing is, what if on this picture I connected, let's say, this point with a point up there and did a whole totally different triangulation, which looks nothing like that. I agree that once you have reached the triangulation, you cannot draw any further segments. Because if you draw any further segment, that would cut an existing segment. This we all agree with. The question is, what if he connected these points in some way that has nothing to do with this picture? Would he obtain the same number of triangles? Not obvious, not clear. Not clear. By the way, if you believe that the second question has the answer yes, has the answer no, that the number never depends on the way he makes the further choices, then you can guess what that number should be, what the answer should be. Because think about it. If he has only one point inside, connected with the 4 vertices, how many triangles does he obtain? 4. And then maybe he adds a second point inside one of those triangles, already existing, and connects that point with the 3 vertices. How many triangles does he obtain in this way? Start with the point inside, connect with the 4 vertices, you have 4 triangles. Inside one of them, take a point, connect with the 3 vertices of that triangle. 6, I would say 6, because it looks like you created 3 more. It looks like you created 3 more, but you lost one of them, because one of them got divided into 3 more. So you increased the number by 2. And then you can figure out, adding a point should contribute 2 further triangles. And you can figure out how many triangles there should be after Peter marks 20 points. But this is only if you believe that the final answer, the final count, doesn't depend on the way he chooses the points and the triangulation. And I'm now more interested in this second part of the question. Why is it that it doesn't matter which points he chooses inside and how he connects them? He has so many choices for that. Why is it that at the end he will always get the same answer? Well, we're going to count a certain quantity in 2 different ways. We will look at the same thing from 2 perspectives. Just like in the first problem, we looked at the number of red marks from the point of view of the cities and the point of view of the roads. Now we're going to count something in 2 different ways. What is it that we can count? Well, something that on the one hand we should be able to count. It should be doable, manageable. On the other hand, it should be related to the number of triangles, because that's what we're interested in. Number of triangles. And remember this problem with the numbers from 1 through 12 on the edges of that cube, when we made this symmetric quantity. From each vertex we added up all the 3 numbers, then we put them all together in one common sum. When you make something symmetric, it is possible to double count. If you do something isolated, you cannot double count that. So here, we're going to double count, that is to say, we're going to count in 2 different ways from 2 different perspectives, the sum of all the angles of all triangles in this subdivision. So for each triangle, you look at the 3 angles, add them up, and form a sum corresponding to all the possible triangles. Okay, this is one triangle. If you add up the angles, you get
42.
42 is the final answer, yes, the final answer will be 42, yes, that's true. But what happens if you add the 3 angles in one triangle? You get 180 degrees. So what is then the sum of all the angles of all triangles? What would happen if you add up, for each triangle you add up the angles, and then what number are you going to get? Well, it is the number of triangles times 180. From each triangle you have 180 degrees. That's just because the angles in each triangle add up to 180. Now let's count this in a completely different way. This is like looking at it from the northern slopes of the valley. Looking at it from another perspective. Let's count the sum of all of these angles in the picture in a completely different way. In a way that does not refer to the number of triangles. What would be an alternative approach to the sum of all the angles in the picture? How can you figure out what the angles add up to? Even now you don't have a number for that answer because you don't know the number of triangles. You're in the process of proving that the number of triangles is whatever, 42, as you say. So compute this in an alternative way. The sum of all the angles. On that picture there are many angles, yes? Excellent, excellent, excellent. Every point inside, the angles add up to 360. I don't know from this point, I don't know how many triangles use this point as a vertex, but if I add up these angles, in this example 4, but it could be 5, it could be more, they add up to 360. So I have 20 points inside, and each of them contributes 360. What is left? What do I have to add as well? Yes?
4 times 90 degrees.
Excellent, thank you. 4 times 90 degrees because of the 4 right angles on the sides. So 4 times 90. And then when I cancel 180, we get the number of triangles is always equal to 42. Regardless of the position of the 20 points and regardless of the specific configuration. You see, you just double counted, you counted from 2 completely different perspectives the sum of all these angles. Yes? If you take a specific configuration of points, well, you still have to divide it into triangles at the end. So if they're all in a line. But if you take a specific drawing, then you can of course compute specifically and you always get 42. You want to know, to be sure, that Peter got 22 no matter what he did with the mark. Okay? Now, consider a grid 5 by 8. 5 by 8 square grid. The question is this. What is the largest number of squares that a line can intersect in their interiors? So now you have the grid 5 by 8. You want to draw a line in a way that you hit as many squares as possible in their interiors. The boundary doesn't matter. If you have a square and you only hit the vertex of it, doesn't matter. Doesn't count. So what would be the largest number of squares? For example, if you take this line, now you just go square by square. Bottom left, then the next one hit is 1 square up, then 1 square to the right, another one to the right, another one to the right, then up. You follow the line and you can compute. It goes through 11 squares. Is this the largest? No. Can you do a line which hits more squares than that? Yes, that's a good comment. We'll discuss that as well. Yes? Yes?
Maybe from the corner on the bottom left to the upper right.
Yes, a diagonal. If you draw a line which connects one corner with the opposite corner, maybe like this, then you can count. It goes through the interiors of 12 squares. Now, I saw one of you showing this. We really have to use very strongly in the proof that we're drawing a line. If instead of a line, you were drawing a curve, well, of course a curve can go through all of the squares. So the difficulty is you have to use that it's a line. And you also have to use that you have a grid 5 by 8. It's not just a question of having 40 squares in the grid. The line definitely cannot hit 40 squares. You can't twist a line to hit 40 squares like that. But in your proof at the end, in your final answer, you want to be sure you use that it is a 5 by 8 grid. If it wasn't 5 by 8, if it was 1 by 40, if all squares were on a line, then of course with one line you can hit 40 squares. Here you have to use that you're drawing a line, and you have to use the specific dimensions 5 by 8 rather than only the number 40, the total number of squares. Okay, so the claim is 12. We can definitely hit 12 squares, but the hard part is prove that you cannot hit 13. There is no way for a line to go through the interiors of 13 squares. How would you prove something like this? It's not easy, it's tricky. It will be again short, but it is a non-trivial statement. You may be finding it obvious. This really means intuitive. Of course, you agree that the largest number of squares would be 12. No line can hit more squares than a diagonal does. But let's prove that it's not possible to hit 13. And here again, our approach will be simply to change perspective. Right now, we're looking at this board, and now we're trying to find a line, or suppose you have a line which hits 13. We're going to change perspective and think about the line first, and then thinking about the grid. Now draw a line, and now think about the grid after the line is drawn. Well, go along the line. Walk along the line and just think about your interaction with the grid, and think about when you enter new squares. Okay, consider a line and traverse it. You start very far away in the line. When you start far away, you're outside of the board. And then you walk along the line. The first interesting event will be when you cross the border of the grid. I don't know if you cross the vertical or the horizontal border, but you cross the border and then you enter a square for your first time. And then you continue moving along the line. You're still inside the first square. At some point, an event will happen, namely, you will cross one of the grid lines. When you cross one of the grid lines, the line will intersect this grid line, and then you enter a new square. So I put a +1 in the count. Then you continue moving along the line and think about how the grid is located. Think about where the grid is. You know the line and you keep moving along the line. Well, again you hit a grid line, maybe vertical this time. Again a +1. You keep moving, hit the vertical, again a +1. Next time, again a vertical. What would happen if you hit at the same time a vertical and a horizontal grid line? What if you go through one of these intersection points? What would happen? Again you enter a new square, you intersect at the same time two grid lines, and you enter one new square. But that's okay. You keep moving. Anytime you intersect one of the grid lines, that's when you contribute new squares. Maybe the next one is again vertical, +1, and so on. So you keep moving along the line. At some point, you crossed a grid line for your last time, so you have a +1 for the last time. And after that, if you keep moving along the line, you're going to escape from the grid. So afterwards, there are no more contributions. Yes?
So what if we take just the left border and we go through 5 of these squares? So after that we have 7 to the side left, because one of the squares are already taken. So we can only go 7 to the right, because
excellent. Yes.
Through the square we can only go 5 down and 8 to the right.
Excellent, yes. So now you're counting how many times we can encounter a horizontal grid line and how many times you can encounter a vertical grid line. Okay, so anytime the line enters a grid line, you enter a new square. Every time the line intersects a grid line, you enter a new square. And now as you're suggesting, let's count how many times a line can hit a grid line, can intersect a grid line. Well, there are two types of grid lines, horizontal and vertical. Well, the line can go through at most how many squares? One from the beginning. The first time you enter the board from the outside, you enter your first square. And then you can enter new squares only with intersections with the interior grid lines. But you're saying, look at the horizontal ones. There are only 4 horizontal grid lines inside the grid. So there are only 4 times where you can possibly intersect one of these and enter a new square after intersection with a horizontal grid line. So that's why up to 4 new squares obtained after intersections with horizontal grid lines. And then, as you say, the vertical grid lines, there are 7 vertical grid lines inside. So you have, the line will have only 7 opportunities to cross, to enter a new square after intersecting a vertical grid line. So plus 7, and this is where the 12 comes from. The 4 is the number of internal horizontal grid lines, the 7 is the number of internal vertical ones, and altogether you have 12 squares. Did we use that we're drawing a line rather than a general curve? Yes, because there are 4 horizontal grid lines, and the line can intersect each of them only once. A line cannot intersect a grid line more than once. So you can have up to 4 new squares after intersecting with horizontal grid lines. And the line can intersect the vertical grid line only once, and that's why you have 7 contributions from there. Did we use that the grid is 5 by 8? Yes, 5 by 8 give rise to these numbers 4 and 7. So that's how you prove that you cannot go through 13 squares. Again, this is changing the perspective. Rather than looking at the grid, a line, and thinking about how many squares a line can go through, think about the line, and then you think about how the grid is built in terms of horizontal and vertical intersections with the grid lines. I finish by encouraging you always to strive for getting this second perspective and also hike the northern slopes of the valley. The southern slopes are best in the fall, but in the summer the northern slopes are also very good.
Thank you. Also, I have to say, I'm proud of you. What you've done here, also the answers, I didn't have any clue, I didn't understand anything, and you gave all the right answers. Also, congratulations to you, thank you very much, and enjoy the rest of the afternoon.